Hello everyone, this is Vijetha, Associate Professor from the Department of ECE from MLR Institute of Technology. Today I would like to talk on integrator using IC741 from linear and digital integrated circuits. So I would like to talk on how an IC741 can be used as an integrated circuit and what are the limitations of ideal integrator and why we are going with the practical integrator and what are the applications of integrator. So, a circuit in which whose output waveform is the time integral of an input voltage waveform is called as an integrator. An op amp consisting of an inverting terminal and non-inverting terminal. Inverting terminal connected with a resistor network and a capacitor network through a feedback towards the output voltage V0. Vi of t is the input voltage which is given to a inverting terminal and OR compensator network has been given to a non-inverting terminal. So, the output of this circuit is given as V0 of t is equals to minus 1 by R1 CF integral of Vi of t dt. Now, we need to check whether the output V0 is an integral of Vi of t or not. So, here this is a node A, let us assume this is a node A and let us assume this is a node B. Now, from this circuit, if you can apply a KCL across node A, the current entering to a node A is given as I, which is the current across the resistor R1, which is equals to IB, that is the current flowing towards the negative terminal of an op amp from a point A, plus IF is the feedback current which is flowing out from a node A towards the capacitor CF, that is IF is the current across the capacitor CF. So, as the gain of this circuit is very high, you can neglect the current IB and you can rewrite this expression as II is equals to IF, that is the current across the resistor II is equals to the current across the capacitor IF, II is equals to IF. So, the current across the resistor can be written as II is equals to Vi of t minus Va of t divided by R1, which is equals to IF can be given as CF into d by dt into Va of t minus V0 of t. By applying a virtual ground concept, VB of t is equals to Va of t, which is equals to 0, and you can rewrite this expression as Vi of t divided by R1 is equals to CF into d by dt of minus V0 of t. So, from this expression we got in terms of differentiation, but we want V0 of t output voltage. So, to get V0 of t, what I am doing, I am integrating, I am applying an integration on both sides. So, you can rewrite this expression as now V0 of t is equals to minus 1 by R1 CF integral of Vi of t into dt. So, finally, you got the expression of an output of an integrator as V0 of t is equals to minus 1 by R1 CF integral of Vi of t dt. If you can write this expression in terms of frequency domain by applying a Laplace transformation, you can write V0 of s is equals to minus 1 by R1 CF. This integral of Vi of t can be given as Vi of s divided by s. So, the gain of the circuit is given as magnitude of V0 of s divided by Vi of s, that is output voltage to the input voltage V0 of s divided by Vi of s, which you can write it as magnitude of minus 1 by R1 CF into s. So, the gain is given as 1 by R1 CF into s. By substituting s is equals to j omega, you can write gain as 1 by R1 CF into j omega. See here in the magnitude itself you need to keep s is equals to By applying a Laplace transformation, this equation can be given as V naught of S is equals to minus 1 by R1 CF into Vi of S by S. The gain can be given as magnitude of V naught of S divided by Vi of S, which is given as magnitude of minus 1 by R1 CF into S. Let us substitute S is equals to j omega, so that you can write the magnitude of V naught of j omega divided by Vi of j omega, which is equals to magnitude of minus 1 by R1 CF into j omega. So finally you can write the gain as magnitude of V naught of j omega divided by Vi of j omega is equals to minus 1 by R1 CF into, so we now get the minus, that is 1 by R1 CF into omega. At omega is equals to 0, your gain will be equals to infinity, where the capacitor acts as a open circuit, which provides, this results providing a negative feedback integrator. So the output of an ideal integrator is given as minus 1 by R1 CF integral of Vi of t dt, and from this expression we determine that at low frequencies the gain is becoming infinity. So what are the limitations of ideal integrator? In the absence of input signal, if you have not given input signal, even though the offset voltage and the bias currents contributes an error voltage at the output, which doesn't produce as a real or true integration of your input signal, and the output waveform will be distorted due to this error voltage, which further limits the bandwidth of an ideal op amp. Hence, an ideal integrator can be used for only at the low frequencies. Because of the small DC offset voltage, this ideal integrator forces to stay in saturation region itself. So, to avoid this, a simple resistor have been placed parallel to a capacitor CF, and this circuit is a practical integrator circuit. So here, let us assume this as node A. Same like ideal integrator, you apply a KCL at node A. Applying a KCL at node A, you can write, let us assume the current across R1 is I1, the current across RF is I2, the current across the capacitor is I3. By applying a KCL across the node A, you can write I1 is equals to I2 plus I3. The current across the resistor R1 can be given as Vi of t minus Va of t divided by R1, which is equals to I2 is the current across the RF, which is given as Va of t minus V0 of t divided by RF, plus I3 is the current across the capacitor CF, which is given as CF into d by dt into Va of t minus V0 of t. And because of the virtual ground concept, the voltage across the node B is 0. So, the voltage across the node A will also be equals to 0, because the voltage across this is very small compared to the input voltage. So, you can neglect this VB and you can neglect the Va also, and you can rewrite this expression as Vi of t divided by R1 is equals to Va of t divided by RF plus CF into, so not Va minus V0 of t divided by RF plus CF into d by dt into minus V0 of t. So, finally, you can write this expression as Va of t divided by R1 plus V0 of t divided by RF plus Cf into dV0 by dt is equals to 0. So, we want the expression in terms of output voltage. So, what I am doing here is, I am rewriting the expression again here, Vi of t into R1, Va of t divided by R1 is equals to V naught of T into 1 by minus V naught of T into 1 by RF minus or plus the expression. I have taken this 1 by RF and the CF towards RHS side, and you can write it as Vi of T divided by R1 is equals to minus V naught of T into, finally I can write this expression as Vi of T divided by R1 plus V naught of T divided by RF plus CF into dV naught by dt, dV naught T by dt, which is equals to 0. And by applying a Laplace transformation, you can write this into a frequency domain. You can write it as Vi of S divided by R1 plus V naught of S divided by RF plus CF into dV naught of T divided by dt can be given as V naught of T, V naught of S into S. So finally you can write the expression as Vi of T divided by R1 plus V naught of T divided by RF plus CF into d by dt into V naught of T. By applying a Laplace transformation, this equation can be given as Vi of S, that is converting into a time domain to frequency domain. You can write Vi of S divided by R1 plus V naught of S divided by RF plus CF into d by dt of V naught of T can be given as S into V naught of S, which is equals to 0. So by transforming this V naught of S into RHS side and Vi of S into LHS side, you can write Vi of S divided by R1 is equals to minus V naught of S into 1 by RF plus S into CF. So Vi of S divided by R1 is equals to minus V naught of S and 1 plus S into CF RF divided by RF. So Vi of S by R1 is equals to minus V naught of S into 1 plus S CF RF divided by RF. So we want this expression in terms of V naught of S. So V naught of S can be given as minus RF divided by 1 plus S into CF RF into Vi of S divided by R1. So V naught of S finally can be given as minus, so finally you can give this expression V naught of S is equals to minus 1 by S into, we got V naught of S is equals to minus RF by 1 plus SCF RF, Vi of S by R1, and we can write this as V naught of S is equals to minus 1 by SCF into R1 plus R1 divided by RF into Vi of S. Just you divide with RF on the numerator and also in the denominator, so that you will be getting it as a minus 1 by SC. So in frequency domain you can write the expression as Vi of S divided by R1 plus V naught of S divided by RF plus CF into S. V naught of S is equals to 0. We want the expression in terms of V naught of S. So I am rewriting this expression as Vi of S by R1 is equals to minus V naught of S into 1 by RF plus CF into S. So you can write this as Vi of S divided by R1 is equals to minus V naught of S into 1 plus RF CF into S divided by RF. We want the expression in terms of V naught of S. So V naught of S can be given as minus RF divided by 1 plus RF CF into S into Vi of S divided by R1. So finally you can write V naught of S is equals to minus 1 by S R1 CF plus R1 divided by RF into Vi of T. So by assuming a RF value is much greater than R1 value and by neglecting the R1 by RF term, you can rewrite this as V naught of S is equals to minus 1 by S into R1 CF into Vi of S. If you can convert this into a time domain, you can write it as V naught of t is equals to minus 1 by R1 CF. Vi of S by S can be given as integral of Vi of t into dt. So, which shows that the output voltage is an integration of your input voltage. So, coming to the applications, this integrator can be used in waveform generating, can be used in analog to digital converters, and also in analog computers they can use the integrator, and they can use this in converting a square waveform into a triangular waveform. That is, you can also use this circuit in triangular wave generator. So, coming to the summary here, today we have discussed what is an ideal op-amp, what is an ideal integrator, how you can use IC741 as an integrator, and how your output voltage will be equals to the minus 1 by R1 CF integral of Vi of t dt. That is how your output voltage is integration of your input voltage, and what are the limitations of an ideal integrator, where you can use this ideal integrator only for the low frequencies. So, in order to increase the bandwidth, you are going with the practical integrator, where you have proved that output voltage is proportional to the integral of your input voltage. And coming to the applications, you can use this circuit for wave shaping circuit, and you can use this in analog to digital converters, and you can also use to convert a square waveform to a triangle waveform. We can say the triangular wave generator. So, these are the applications of an ideal integrator. Thank you.